Hello, I'm member number one, Amin Kutsi, bioengineering, biotechnology major.
Hello everybody, member number 2 here, Jose Zaragoza, bioengineering major.
Hi, my name is An. I'm team member number 3. I am a bioengineering biotech major.
Hey, I'm Alan. I'm team member number 4 and I'm a bioengineering major.
Patient X has just been diagnosed with chronic kidney disease. They have 3 options: get on the donor list for an implantable kidney, peritoneal dialysis, or in-center hemodialysis treatments. If the patient chooses in-center facility treatments, 25% of their free time will need to be spent at the in-center facility.
And so patient X will have to go to the hemodialysis center for 3 times a week, 4 hours each day, be connected to the stationary machine as 5 times their blood volume is being filtered, and undergo a heavy pill burden alongside restricted daily diet and fluid intake.
This problem doesn't only plague patient X, it is also the daily life for 3.4 other million Americans. They have to schedule their entire lives around their next treatment, and hemodialysis isn't cheap either. It ends up costing U.S. taxpayers up to 7% of the U.S. Medicare budget.
Therefore, in this senior design project, our team have tried to develop a wearable artificial kidney device in a form of a BWAKpack based on the principles of hemodialysis in order to overcome the limitations of the conventional dialysis treatments that burden millions of patients with kidney diseases.
This is the original design concept that was created in order to transform the hemodialysis unit into a wearable version. We have a solar paneled backpack that will serve as the battery storage. We have pouches and dividers to hold our electrical components. The main filtering component will be a hemodialysis dialyzer that will be strapped underneath the backpack. We propose a design with double lumen catheter as our primary source of vascular access.
And so our proof of concept prototype is the backpack containing the components of an in-center hemodialysis machine. As you guys can see the components here. For starters, we have the standard dialyzer that is compatible with our low flow rate fluid system established by our circuitry, and is connected to a holding tray that fits everything into one pouch of the backpack.
This circuit uses 2 peristaltic motors to circulate a dialysate solution and the patient's blood. It also has a detachable power supply for replacement.
3D printed the electrical box to keep all the electrical components in a fixed place. Inside the box, there are an Arduino breadboard and electrical wires supplying a voltage of 3 volts to control the desired flow rate of the motors.
So there it is. We've taken the first step in addressing the third most pressing need identified by patients undergoing in-center hemodialysis, which is the inability to travel.
Our device offers extended low flow rate technology that is slower but more physiologically relevant and mimics the kidney's function in filtering the blood on a daily basis. We think that our device can offer a better treatment than the in-center kind of rushed and aggressive treatment that hinders patient mobility and decreases their treatment satisfaction.
So in the future, we hope to implement a new material called MXine as a absorbent in the regeneration system to reduce the weight of the device, and also to design a secure vascular access that minimizes infection, and lastly,